Right, energy stores. You need to know what all the different energy stores are and give some examples of them so that then you could describe whether energy was in that store at the start or the end in any description. I think the best way to remember lists of facts, so obviously we're using flashcards to remember definitions, but if there's some sort of link to them, we can use something called a mnemonic to help you remember them. You can use the mnemonic geek cement to cement these terms into your memory. Now if you're following along, you've got this handout with all of these written on them for you to follow along and fill in as we go through it. The first one is gravitational potential energy. Gravitational potential. So all of these are the energy stores. Okay, so what is this going to be for then? Well, this is any object lifted above ground level. Your gravitational potential energy store increases when you go up the stairs. It decreases when you go back down it. We now know that lifting this 100-gram apple, so that's 0.1 kilograms, up by 1 meter, we give it 1 joule of energy. We now know that that joule of energy has gone into its gravitational potential energy store. So 1 joule extra in its gravitational potential energy store. We'll go into the calculation to work this stuff out in a future lesson. K is for the kinetic energy store. Think of kinetic like Microsoft Kinect or something. Kinos means movement in Greek. So anything to do with kinetic is movement. So any moving object. This could be a football being kicked, a car moving, a person running. Literally anything that's moving has kinetic energy. And again, there's an equation that we'll have to do with that in a future lesson. And the next one is C. This is chemical energy. Chemical energy store. Examples of this are, it's released when something's burned. It's in fuels, like fossil fuels. But also, the other ones that people tend to forget are batteries and food. So batteries and food and fuel have energy in their chemical energy store, which can get released when they're put in a circuit or when you eat it and you do respiration. And we've got the elastic potential energy store. So quite often also called the elastic potential energy store. Where's this? Well, in a stretched elastic band. A bow and arrow, for example. Bungee jump, when the cord is stretched down to the ground. So that's in the first E. Now M stands for magnetic energy. The magnetic energy store, like for example 2 magnets that are separated, they either attract or repel. Then we've got the next E for electrostatic. Two separated charges that are attracting or repelling. Then we've got nuclear for this last penultimate one. So the nuclear energy store, released through radioactive decay. In nuclear fission or fusion. You study those again in a later topic. And the final one here is thermal energy store. But also Quite often, some textbooks, you'll see it also called this internal energy store. So I suppose that's because the particles themselves, when the energy is in the thermal store, the particles move around a lot more, so their internal energy increases. Again, we'll look at a little bit more about that. In terms of gases, when the gas's thermal energy store increases, the kinetic energy of the particles increases, so the internal energy of the gas goes up. Really, this is the energy an object's particles have because of its temperature. If an object is hotter, it will have more energy in its thermal energy store, so in its internal energy. Now, the thermal energy store is probably the most common on exam questions because it's where energy all ends up. It normally ends up in the thermal energy store of the surroundings. So whether it's the brake blocks of the car and then the air, whether it's the room, in the example we had for the cup of tea. So it always ends up in the thermal energy store of the surroundings. For those of you who have heard of this, this also leads to something called the heat death of the universe, which is as energy keeps on spreading out, it dissipates and dissipates further and further until eventually all the energy from the stars in their concentrated form spreads out again into the surroundings, dissipating, spreading out until eventually there's no energy left in any concentrated form. No process in the universe can take place, and that would be called the heat death of the universe. A happy end to the universe for us all. That is all the energy stores then that you need to know. Remember, use geek cement to try and remember those, like mnemonic. And now we're going to have a look at the methods of transferring energy from one place to another. There's only 4 of these, so let's learn this next. Let's look at the 4 ways of transferring energy, sometimes referred to as shifting energy from one store to another. So we're going to use mehr, as in more in German, to help us remember this, M-E-H-R. So more, or mehr in German, is the way to remember the ways of transferring energy from one store to another. M stands for mechanical working. Work has a definition in physics, but essentially mechanical working is when a force acts on an object through a distance and that transfers energy from one store to another. So for example, you kick a ball, when you put a force on that ball, you transfer energy from the chemical store in your body, in your muscles, to the kinetic energy store of the football. E stands for electrical working. This is the way of transferring energy through an electrical circuit. So whenever a charge moves through a potential difference, energy is transferred from one store to another by electrical working. So for example, you've got a light bulb in a circuit, transfers from the chemical store of the battery through electrical working to, for example, the thermal store of the wires. H stands for heating. So we discussed this, but whenever 2 objects are at a different temperature, energy will flow from the hotter object to the colder object by heating until those 2 objects are the same temperature, and then they're in thermal equilibrium and there's no more energy transfer by heating. R stands for radiation. So this is energy transferred in the form of sound or light or microwaves. So any of the electromagnetic waves, again that's another topic we'll study. When I'm talking now, there's energy transferring via radiation, so sound waves, to the microphone that's picking this up. There's light transferring from the sun, so that's transferring by UV, by X-rays, visible light, infrared. All of those are energy transferring from the nuclear store of the sun by radiation to the earth. You need to be able to describe the energy changes in everyday situations. So in other words, the exam question will tell you a certain situation, and you've got to describe the changes in the energy stores as that change in the system happens. So for example, you're riding your bike on a flat road and you're pedaling and accelerating. What are the changes in the energy stores? As you get faster or accelerate, your chemical energy store of your muscles decreases and the kinetic energy store of you and your bike increases. The specification states 4 different examples that you need to know and be able to describe the energy changes for. So the first one of these is just an object projected upwards. Okay, so if you throw an object up into the air, describe the energy changes that happen during that process. So just watch this ball as it's projected up into the air, and then just consider what are the changes in the energy stores then. As the ball starts low, it doesn't have very much gravitational potential energy, so all the energy is initially in the kinetic energy store. As the ball leaves your hand, the energy is in the kinetic energy store of the ball. Now, as it gains height, the kinetic energy store decreases because it's slowing down, and actually when it gets to the very top it actually stops for momentarily before it then starts to speed up as it falls back down. So as it leaves your hand, the energy is in the kinetic energy store. That decreases and the gravitational potential energy store increases until at the top of the flight there's no energy in the kinetic energy store of the ball. It's stationary at that point, and all the energy is in the gravitational potential energy store of the ball. Okay, now for that particular example, that's all you need to know. So the kinetic energy store decreases and the gravitational potential energy store increases, with it being all in the gravitational potential when it reaches the top of the flight. Okay, and there'll be zero kinetic energy at that point. Let's have a look at the second statement from the AQA specification, which is describe the energy stores when an object falls, hits the ground and doesn't rebound. So what are the energy changes there? Well, again, I'm going to use one of these juggling balls to do that. So if we drop it and just see what happens this time. It's sort of the opposite of what we've just talked about. So the object starts with energy in its gravitational potential energy store. The energy in the gravitational potential energy store decreases and the energy in the kinetic store increases. Then though, it hits the ground. So if it's at ground level, there's zero energy in the gravitational potential energy store and there's zero energy in the kinetic energy store because it's not moving. So where's the energy gone? Remember, we're looking at a closed system. The energy can't have been destroyed. It's got to be somewhere. So we try and rack our brains through the other energy stores that it might be in. So let's run through the geek cement. So it's not in the gravitational potential. It's not in the kinetic. The C, it's not in the chemical energy. Now, elastic potential energy, now if the ball bounced back, yes, then it would have gone into the elastic potential energy and then gone back up into the kinetic or gravitational. But if it's not bouncing back, it's not gone into the elastic potential energy store either. Magnetic, well, it's nothing to do with magnets, so it's not going to be that one. Electrostatic energy, it's not to do with the charged particle. N, it's nothing to do with the nuclear energy in this example. So it's got to be T, it must have gone into the thermal energy store. It's the internal energy of the table and the ball. So the energy eventually has gone into the thermal store of the ball and the table, raising the temperature of both of those two. And so this ball's got a mass of 120 grams, so we'll just call that 0.1. So it's the same as the apple. So if I lift it even to the top of this, the height of this room, we're only talking sort of 3 or 4 joules of energy. So when it falls, that 3 or 4 joules of energy isn't going to heat the table up hugely, but we can still see if it had any impact at all. So it'll be interesting to see whether it has. Let's have a look at what happens when we look at the image through an infrared camera. So you can clearly see the heat of the ball there gradually dissipating back to the room temperature. Let's show it again. See the temperature just increasing. You can see the slightly raised temperature where the ball had an impact. Obviously the more energy the ball had released when it came to a stop, so if it's something like a bullet, and this is how it works with cricket bat technology to see whether somebody's out and see the ball actually hit the bat or not. They use the infrared camera. The energy will have been absorbed into the bat from the ball, and then the thermal store of the bat will increase, and you'll see that as an increase in temperature, and it'll emit more infrared energy because its thermal store's increased. That's the end of the first topic of AQA Physics on energy stores and systems. So you now know what a system is, you know what the conservation of energy is, you know what a closed system is, you know the energy units, you know how to name all the stores of energy, all the different ways in which energy can be stored. Examples of those, you know the 4 ways in which energy can be transferred from one store to another, and we've also had a description of a number of situations in which a system changes, and you can describe the energy transfers in each of those situations. In the next section we'll look at calculating the amount of energy in the stores. So in particular you need to know the equation for kinetic energy store, the gravitational potential energy store, and the elastic potential energy store. You double the speed, what happens to the amount of energy in the kinetic store? Find out in the next video.